Hello, I'm Sylvia Oakland, and welcome to AI GovCast. Federal leaders are working on the next Manhattan Project as they work to stand up the infrastructure and autonomous capabilities needed to rapidly test, validate, and scale AI research following the launch of the Trump administration's Genesis mission in November 2025. Led by the Energy Department and its 17 national labs, the Genesis mission aims to create a national discovery platform that connects supercomputers, AI systems, and quantum technologies into an integrated infrastructure. Today, we're joined by the Argonne National Laboratory, one of the first U.S. national labs to adopt digital computing for scientific research. And 80 years later, they're playing a pivotal role in the Genesis mission. And here to tell us more is Argonne's Rick Stevens. Rick, thank you so much for joining us today.
Thanks, Sylvia, for inviting me. Happy to be here.
Yeah, so why are people comparing this Genesis mission to the Manhattan Project? Do you mind level setting what that looks like?
Well, I think they're comparing it for a couple of reasons. One is that the Manhattan Project, of course, was the origin of the labs. And so it has a special role in the narrative around why the labs exist and why the concept of a national lab complex exists to do big things. And so, in some sense, it's the DOE version of a moonshot, right, for NASA. So it's the way we talk about the something big that is kind of requiring everybody to work together on it. So that's the kind of abstract, reason for it. But there's a more concrete reason. When the Secretary of Energy joined DOE in last year, he started talking about Manhattan Project for AI, and that terminology kind of stuck a bit. But I think, given that AI is a very different kind of thing than a nuclear weapon, there was a desire to change the name and to create its own kind of identity. So that's the backstory behind it. It really is a massive effort, and part of the reason for talking about it that way is to communicate that this is not only an important thing, but it requires everybody to work together.
Yeah, and I think another thing that becomes really important is why now, right? I know we've seen so much interest in AI, whether it's generative or agentic, but why is this all kind of coming to a head now for the Department of Energy and the labs?
So the DOE labs have always had some engagement on AI research going all the way back to the 50s and 60s. Even at Argonne, I mean, I came to the lab to do AI related things in the 80s. But of course, since 3 or 4 years ago, with this last wave of modern generative AI and large language models and kind of the enormous progress over the last 15 years or so, it's become obvious to many people that it's a huge lever on everything that we can do, whether it's productivity in daily life or whatever, but also in terms of scientific research. And so we're at this kind of inflection point where AI is good enough, has become good enough, in many cases, amazingly good, that it's a capability that you don't want to not use in scientific research, engineering development, and so on. So there's a opportunity of bringing these two things together. So that's part of it. I think the second part is that we're in a global competition, and there's enormous progress being made outside the country, and there's an urgency to connect all the dots and to leverage the amazing ecosystem we have in the United States with the amazing infrastructure of the national labs and the breadth of the universities and the industry base in the US to do something that only we can do. And so that's kind of the realization. I mean, this is, I think, Dario's vision is that we have a window of pulling everything together. And if we do it well, we can accelerate the US capabilities dramatically, accelerate time to solution in all kinds of areas of science, but also increase broadly scientific impact and scientific productivity. So there's an urgency, partly because of the international competition, partly because of the opportunity and the fact that general AI capabilities are continuing to advance at an amazing rate, and we need to get kind of on that wave and ride that wave as opposed to have it just happen, separately from what we're doing. So I think there's many reasons why it's urgent. The labs have, of course, been trying to strategize on how to do a large-scale AI initiative for about 6, 7 years. We had various large-scale town hall meetings and rallied the community around it. But I think it was the current administration and the leadership that we have, especially with the Secretary Chris Wright and Dario Gil, that pushed it, over the edge to where we could actually get something going.
Yeah, and I think that then kind of brings me to this idea of each of the labs focus on different application areas, right? And so do you mind diving into a little bit about how the Genesis platform is going to have this most impact on what your mission is at Argonne?
So different labs, depending on what programs are their primary basis, have different missions. Although Argonne is a multi-program Office of Science lab, so it has considerable breadth, similar, for example, to Oak Ridge and Berkeley and to some degree
Mhm.
Brookhaven and PNL. And so it's not like we have one project. We have dozens and dozens of projects. The platform that Genesis is building is aimed at creating a baseline capability that everybody can build on top of that reduces the amount of duplication that labs would have to do if they were all doing this separately. And also, from your introduction and also from our plan, is to integrate things. So if I have a problem that needs a supercomputer at Argonne and needs a neutron source at Oak Ridge and needs some instrumentation, say at SLAC or something, the platform would allow me to build that application, have AI orchestrate all of that in a seamless way. So it gives us something that we don't have today, which is the ability to conceive of using all of the assets of the Department of Energy on a problem. But of course, we have hundreds of problems. So the Genesis mission proposed a set of lighthouse problems, or what we call national challenge problems, that was just released a couple weeks ago. There's 26 big challenges there, and then there's others that are not on that list. And these represent kind of the big major thrusts of the Department of Energy, where we believe there's huge opportunity to go faster and to move with more impact from the use of AI. So those problems include things like accelerating fusion deployment on the grid, or to reimagine how the grid's going to operate, or to design quantum materials using AI for specific properties, or discovering, say, new quantum algorithms, and so on. So there's many areas. The way that we've organized teams in Genesis, we have these what we were calling lighthouse teams or national challenge teams, science technology challenge teams. There's dozens of these teams, and each team has some goal. Like one might be to improve our ability to find, say, critical minerals, like in the U.S., for example. And that team has many labs as part of that team and brings many different disciplines together. It might bring people that have an understanding of the subsurface, resources, the ability to use remote sensing data, to combine AI to integrate that knowledge and to understand the mineralogy and so forth. So many of these problems have big interdisciplinary teams. And the part of the vision here is to connect domain experts or discipline experts with AI and computing and math experts to form these kind of interdisciplinary teams that are well positioned to leverage the advances outside the department and inside the department on AI to the specific problem area. And so that's kind of broadly how it's structured. Now, of course, some labs have special target missions. Like, for example, the Idaho National Lab is focused on nuclear fission research, and they lead the effort to integrate AI into accelerating, the next generation of fission reactors. And Princeton Plasma Physics Lab leads in the fusion program, and they're leading the effort to bring AI to that. But these are kind of labs that have special missions. Labs like Argonne, Oak Ridge, Berkeley have many programs in science, energy, technology, national security, and so forth. And our portfolios are quite broad. But the three labs that I mentioned, Argonne, Berkeley, and Oak Ridge, we also have the open scientific supercomputing resources for the department. So one of the roles that are special for us is not just the breadth of the science thrust and so on, but we're on the science side responsible for integrating the supercomputers and the instruments like the advanced photon source at Argonne, advanced light source at Berkeley, the neutron source, SNS at Oak Ridge, and other resources like at Brookhaven, the EIC and so forth that's being built, into the platform. And so there's in addition to the kind of science applications and the platform component that has, say, AI models and data, there's also a big effort around integrating like computing resources, but also instrumentation. And depending on which lab you're at, you have different combinations of those things. And so, given application projects that might, be hosted there, they might have a special connection to those resources. But the way to think about it is that we'll have dozens and dozens of teams across the labs that are arrayed against these grand challenge problems. And those teams will consist of multiple labs, university partners, industrial partners, depending on what they are. And those teams will evolve and grow over time to attack those problems.
Yeah, and I wanted to pull on that thread just a little bit. Is there any specific projects? I know that you're working on quite a few at Argonne, but are there any that you can kind of detail what it looks like connecting some of that data and those computers together? I know there's been a couple announcements as well, just working with, like you mentioned, industry partners.
Sure. Well, one of them is got a nice name called Synapse, and it's a collaboration among the light sources and these, like the advanced photon source and ALS, and they're building AI tools that can image materials or structures, say 10 times faster or 100 times faster with 10 times the resolution. And AI, so what AI is doing is it's increasing the productivity of the underlying facility by at least an order of magnitude by leveraging AI techniques, say, in accelerating the imaging. So that's like one that's, of course, close to home. Another one that we're involved in that we lead is in microelectronics. And the idea here is to look at all the things that have to work when you design a new chip design or a new process in microelectronic stack, or maybe introduce a new materials or a new device construct in there, all the way up to maybe a new architecture. So you have this whole vertical stack of design decisions you have to make or choices you have to make. And the way that the community currently does that now is through a process called co-design, where you kind of do simulations to try to make decisions, and then you do feedback, and it works, and it's what the community's been doing for the last 20 years or so. The idea that we have with that is, can we use AI to not only accelerate that process of co-design, but reimagine the process of co-design so that AI plays a much bigger role in sorting out the options, the choices, the alternatives, and making sure everything works together when you're doing an experiment, computationally or whatever, to the point where the ability for us to move faster in designing novel microelectronics becomes possible, right? And that's because we have a material science team at Argonne. We've got a computer science team. We have collaborations with other labs and universities in computer architecture. We of course have applications. We've got a supercomputing, so we have all kind of the pieces to put that together. But we have many other projects. Critical minerals I mentioned. One that I'm very excited about is called Quarks to Cosmos. And in that project, I mean, it's a collaboration across multiple labs. The idea there is integrating the observational data from cosmology, from high energy physics, from nuclear physics, and theory data or theory information and theories with simulations, and trying to use AI to integrate all of that into a single framework that allows you to explore hypotheses, say dark matter hypotheses, that can connect up with everything that we know. Now that's very ambitious, but the high energy and nuclear physics communities and the cosmology community has been thinking about that for many years. In fact, if we go back to the original AI for Science town halls that we started back in 2019, that group got up and said, their vision was to integrate all known physics data into a massive, AI system and use it to try to make forward progress on the fundamental challenges in physics. And it was very visionary, back in what, 8 years ago, whatever it was, 6 years ago, 7 years ago. And now we're starting to see headway on that problem. I mean, in that community coming together around that idea. And so, that's a really amazing thing. And that's not going to happen spontaneously in some, small place, and it's not really something that a company is necessarily going to do, but it does require collaborations across universities, national labs, the big high energy physics collaborations like CERN and Fermilab and so on. So that's an amazing project. Another one, there's just lots of them. It has a funny name. It's called Moat, but basically it is a collaboration among the people that build particle accelerators, or just accelerators, not just particle accelerators, but accelerators that are used in science. So yes, the high energy physics people that build like the colliders and so on, but also the people building storage rings for light sources and LINACs for the neutron source and so on. And the whole idea of that project is to integrate the combined experience of people that have built and operated accelerators for the last many decades, such that there's an AI companion that can help run the accelerator, that knows everything that's ever been done in running accelerators, because accelerators are very complex machines that have nonlinearities in them, have thousands of sensors, and they often require tuning by humans, by the human operators, to keep them going. And the idea here is that we can build this AI companion that helps every team that's operating an accelerator that has the combined knowledge of all the teams, which is now not possible. But if we can do this, right, we can have AI act as a helper across the whole complex. And a lot of accelerators are, of course, also used in industry. So that's like an amazing thing, right? It's kind of like building a collective consciousness around that kind of domain. And if you take that idea a little bit forward, you can think of applying it in many other areas. Like, for example, you want to do materials design. Well, what you'd like to have is an AI that knows about every previous materials design experiment, and it has enough computational power and enough access to simulation models that it can do kind of thought experiments, with its users in some sense at a scale that individual researchers can't do today. So every one of these areas, these grand challenge areas that we think about, has an opportunity like that in it.
I think this is where, for me, it really gets fascinating because there's so much information and there is such a potential to get this moving. Some of this stuff that you're describing sounds like it is straight out of a science fiction movie or book, and it's so incredible and like you said, very, very visionary. Even now.
Well,
Um,
these ideas, in most cases, these ideas aren't new. I mean, in the fundamental sense, right? And that people have been thinking, but wouldn't it be great if we could do X, Y, and Z? What's different now is that we can kind of do that. And the the graded, the advances by the Frontier AI labs and the open models and so on are giving us the foundational tools and the foundational systems that allow us to go back to those visions that we had in the past about how we might want to think about doing this and now actually make it real. So that's the super exciting part about it, is that what AI does, and this is not just in science, I mean, this is true across the board. It gives you the means to imagine something that you couldn't do in the past that maybe you can do now, right? And this is, I think, what's so exciting about it in the most general sense, is that it empowers us to imagine new ways of doing things, and not just the imagine, but the actual building of the system that can do that.
you have answered so many of my questions, and this one I hope is definitely a softball, but what are what are you looking forward to in the next I'm going to say like 6 months to a year, just keeping it very short term. What are some of those either goals or just milestones that you and Argonne are looking forward to achieving?
In a month or so, we have an initial set of early what we call demonstrations of some of these AI adventures, I guess if you want to call them that. So there's going to be quite a few of these at the end of March that will give, I mean, we'll make them public at some point, people a sense of how much progress has been made in the last 6 months on this problem, or on this broader set of problems. I think over the next 6 months or so, beyond that, we're seeing, in some sense, a aggregation of interest from companies and universities and labs into a more coherent community that's dedicated, that's intellectually dedicated to this idea of building a scientific superintelligence or a massive infrastructure for science, AI infrastructure for science. And as we start connecting the pieces together, new things will become possible. And it's kind of like, I don't know, you're building a big Tinker Toy, problem or something, and as you start connecting things, it gets more exciting, and as you connect more things, it gets more exciting because more things become possible. And so I think we're going to see that kind of spontaneous kind of excitement building as we start getting all these things connected together, and the ability to use the things that are connected is not coming from people having to write, like personally, like writing tons of code to do that. So the fact that AI can help us do all that integration, and we're already starting to see that. I mean, that we've got, existing pilot efforts now that are connecting resources across the labs, doing model inference at one lab, running a simulation in another lab, designing an experiment in another lab, and it all happens kind of automatically, and it's very cool. I mean, every time we see this, it's like really cool. And, we're kind of hoping that as these things mature and they become less of a demonstration and more of an actual tool that people can use, and we get more and more people exposed to this, that there'll be this kind of collective aha moment, right? That people start realizing, researchers across the board start realizing that we're entering kind of a new world. And I'm looking for that aha moment. Not for me, because I've already had that, but I mean, it's kind of like across the board. And I think that's the exciting thing. That's not like a technical thing. That's like a more of a social realization of where we are. But I think that's on the horizon. And then, almost every day there's new AI things being released, right? And it's great here in the US. We have these amazing frontier AI research labs that are in competition with each other. That's a forcing function of innovation. And then we have things happening from outside of that also that challenges, what's possible. And so, in some sense, just being part of this, wave of moving everything forward is worth it. I mean, even if much of what we're trying to do will take longer or is harder, in some sense, that we're not discouraged by that because the rate of progress is not slowing down. And every time there's a new broader capability in the broader AI world, we figure out some way of leveraging that in the scientific space. So it's all very exciting. I don't think there isn't a day that isn't exciting on this space.
I'm so glad to hear that because I cannot wait to see what comes out of it. Once this announcement was made in November, I was looking forward to speaking with the labs and just learning how you all are working together, what all of this is going to look like, and what it's looking like on the ground when it's up and running. So, Rick, thank you so much for joining us on the program today.
Thanks, Sylvia, for having me. Take care.